in a debris, influence of fracture mechanical graded materials on the correct propagation behavior in three-dimensional structures. Please.
Thank you very much for the introduction. Dear ladies and gentlemen, as you remember, my name is Catherine Dibby. I work at the Institute of Applied Mechanics at the University of Paderborn in Germany. So I'm pleased to inform you about my lately results of my research field using functionally graded materials. So first of all, I want to explain what I understand by using functionally graded materials. And also I will point out some challenge about the 3D crack growth using this kind of material. Also I want to present you my new concept for this functionally graded materials to predict the crack growth, taking into account the grading of materials. Therefore, I also implemented this concept into an already established simulation program, and with that I did some simulation examples I want to show you as well. At the end, I will end my presentation with a short summary. So, first of all, functionally graded materials are characterized by locally different material properties. So it means that due to expected stress on my structure, I will vary my material properties. As you can see, there is an example like a cogwheel. So on the outside of my cogwheel, on the plank tooth, I've got different material properties due to higher wear resistance. And in the inner side, here it's called like light green, it's different. So it's like not as high as it was before, because in this cogwheel, we had some kind of heat treatment. So depending on the manufacturing process, we can have now in one component two different local areas with different material properties. And it can happen now that either you've got some kind of sharp transition area, as you can see here, or you can have some kind of continuous transition area. So this means that the material properties from this area to this one here will change as in the jump. Also, you could say there are, say, three different kinds of grading materials. Some kind of what called fracture mechanical grading, some elastical grading, or some kind of a combination of the first two mentioned gradings. So in my research field, I only handled taking fracture mechanical change into account. So what does it mean? Really it means that for each local area, I've got different fracture mechanical properties. So as you can see in this kind of velocity curve, the fracture mechanical properties important are the threshold as well as the crack toughness. So the more this curve lies on the right-hand side in such kind of diagram, I'm talking about saying the favorable area or the most favorable area, because the material properties are better for crack propagation. This purple one here, therefore, is the unfavorable area. So now we know that we can have different properties. It could be really good because of the use of the structure, but also this has an effect on the crack growth. So therefore, my target was to characterize when and how does this functionally grading will affect my crack path or crack growing. So therefore, we'll just give a small hint about crack growing. Everybody should know by now that you can declare three different kind of modes using homogeneous isotropic materials. So homogeneous isotropic means that in all kind of directions and in all points of my structure, I've got the same material properties. So therefore, we can use something like mode 1. So it means the force perpendicular to the crack plane. Obviously, then the crack will grow in crack plane direction. Same would be like mode 2. The direction of the force is in crack plane. So therefore, there will be some kind of kinking angle preaching. So this would be around about 70 degrees. So, but this is no longer the case when you use something like called functionally graded materials. There also you have to take into account not only the stress occurring on the crack front, but also you have to take into account the local material properties as well as the inclination of the material grading transition. So this here I will call VM for the future. So we found out with some experimental investigation that there is sometimes influence on the crack path and sometimes there's not. So how could that be? Let me show you. Oops, not going. Okay. Like on this example, mode 1. So I put a grading transition in here, and now it could happen that as soon as the crack grows and reaches my transition, that the crack won't grow in the same direction anymore, but therefore it will turn to grow along this transition grading. But sometimes it just doesn't affect the crack path at all. So now the thing is, when does what happen and how can I explain it? Therefore, I used already established criterion for 3D crack growth, so-called sigma 1 dash criterion. It was established at our university. And this criterion just gives a hint about the crack propagation is in radial direction, starting from the crack front, obviously. And the crack propagation is perpendicular to the maximum stress sigma 1 dash. And therefore, you can get an angle called phi here. Also, if you say calculate the stress intensity factor Kb using this maximal principal stress sigma 1 dash, you can also give a hint about when does unstable and stable crack growth will appear. So this is the basic of my new concept. And now I don't want to go into detail, I just want to show you a quick overview how my new concept is going to work. So therefore I've got this kind of structure, it's got a crack here. This crack just reached the transition. So I've got two material areas, and obviously if you look at the crack front, there will be some kind of material function. This part here I use the threshold. So you can see there's a jump between this area and this area, obviously because there are different material properties. So now what I need is a relevant stress function. It gives me a hint at what time does this crack will grow at all and in what kind of direction. So this hint is now when it's the first contact with the material function. So it's really easy said, but how do I get this function now? So therefore I plotted three functions. So first of all, here again, the material function I've shown you earlier on. You can see there's this jump at 30 degrees. So it means I've got a transition grading at an angle of Phi 30 degrees. So the next two thing was I calculated stress functions using the possible kinking angles Phi and Phi nil. So as you can see here, they've got a contact with the material function. So on this part here and here. So now I know that soon as this material function is reached, then there will be some kind of crack propagation. It's like a party crack will start. So you can see here, the pink one here is the first one to reach the material function. So therefore, this here, 30 degrees will be my relevant stress function. So when I've got now material function and relevant stress function, I also need to know what is really happening at the crack front. So therefore, I need to calculate the real stress using the Kb intensity factor. So as you can see here is in red, shown here for this crack front. And as soon as this red function is greater than the orange one, so the relevant one, then I know, okay, in this case here, with this situation, I put a load on everything, then there will be some kind of crack growth. If it's not greater, then the crack will stop. It won't be any kind of vertical crack growth at all. So as you know, sometimes crack growing can be really difficult to do by hand. I used a simulation program and I implemented my concept into this program. So therefore, it was like other crack 3D, and I invented a bit more into it, so it's called now version KB50. So how does this program work? So first of all, you put some kind of necessary entities inside, like FE model, formal structure, and the crack, as well as some parameters, obviously. In the NetAdapt module, NetAdapt 3D, you will create some FE model including a crack and a submodel for the next simulation. So Abacus will solve my problems now. So this two FE models will be solved in this FE solver. Afterwards, the information will be passed over to the module called NetCrack 3D, and here the calculation of the crack will be propagated. So I had to put in some new entities, so it is now possible not only to calculate homogeneous isotropic structures, but also functionally graded structures. Therefore, I had two main steps I had to do. So first of all, the program had to learn how to cope with this information. So by putting in my FE models of my structure, obviously it will have the information inside of all materials, everything locally. It learned how to find the local transition and the local grading angle. The next thing was like in this NetCrack 3D for the fracture mechanical evaluation. So after calculating the stress intensity factors, as everybody should know, it was done at K1, K2, K3, and KV. Afterwards, I put in my new functions, so to make sure that the crack will really grow in the correct direction. So obviously, I did some simulation, and here is some of them. First of all, a contact tension specimen. So I had a grading in here for about 40 degrees. So this is my unfavorable area, this is my favorable area, and here's the crack initial. So now, two simulations been started. When I start in my unfavorable area, then soon as the crack grows and reaches my transition, then it happens that the crack will change the kinking angle and will grow along this transition. But if I change now the area, so starting in the favorable area, then the crack will just grow through it and just don't mind at all. But that's only how it seems to be. Because
Katarina, 3 minutes.
You can't only look on the crack path itself, you also have to look on the lifetime expected. So as you can see here, I had 4 different simulations. Homogeneous, unfavorable, favorable, and 2 material grading, just changing the material areas. So you can see there's always kind of influence on the crack growth, because here you can see the load cycle, they vary a lot between these 4 different simulations. Now, as you could look at like this contact mixed mode specimen, everybody would say, oh yeah, that's easy. You start in the unfavorable area, and it goes to the favorable one. Obviously, then the crack path will change. If you turn around, then the crack always will go through it. So what's the hint about this? But that's not so easy. Obviously, I tried something different. So I changed the local transition angle. Like here I had minus 75 degrees. This one is 30. And now you can see, even though I changed the local area properties, there's no influence on the crack path at all. So the aim of this is now, you have to look for not only the stress occurring at the crack front, but you also have to take into account the local material property areas, as well as kinking angles, what I mean the local kinking. So like for this transition area, obviously it won't be 30 degrees because the crack already had kinking down, so this grading VM now would be around about 90 degrees. So that's big influence on the crack path as well. So now I come to my summary. So what did I show you today? I tried to explain to you how the new crack growth concept is working using graded materials and taking every possible items into account. Therefore, I showed you some implementation way in the simulation program called AdaCrack version KD15, and then I shown you some of my simulated examples. I hope to understand that obviously these are some easy examples. I made some fun with not only a sharp transition but also a continuous transition, but because of time I kept it out. So now I will say thank you very much for your attention.
Thank you very much. It was very interesting. I will have questions to you later.